As I promised in the previous video, I'm going to discuss problems, particularly problems from fundamental theorem of calculus in this video. When I started the exercises, I found that these initial questions called getting started in this book are very good for conceptual clarity and also to set the basics right before we do more numerical problems. Okay, so I'm beginning with them. Suppose A is an area function of f. What is the relationship between f and A? Okay, so here the understanding is that the antiderivative is the area function, right? But how do we exactly express it? We say that the area, you know, as a function of x, right? To give you full clarity, let me actually also draw the diagram. This is the function, right? And let's say this is the point from where I'll start counting, measuring my initial point. And then let's say this is a variable point x, and that's the graph of the function f of x, right? So the meaning of the area function is area, this, area function gives the area from point A up to the variable point x under the graph of that function f of x, right? So the area is the integral from a to x of that function f of x. But because we are using x as the integrating variable or the limit, we don't use x within the integral. We use another dummy variable t, or you can use any other variable f of t dt, meaning t itself is another variable but not really another. What we mean is t is a variable here that takes its values from a to x, right? T varies from a to x. And as we integrate that, we get the area under the curve, which is the, now that x can change, right? So that variable area we get is the area function. Okay, that was first question. Suppose f is an antiderivative of f, small f, and a is an area function. What is the relation between the antiderivative and the area function? Again, we know that, right? This area function gives you the area with respect to a particular starting point. Okay. When I define an area function, I choose a starting point and the area under the graph is measured starting from there. In general, for an empty derivative, that starting point is not fixed, right? And hence we have that arbitrary constant c in the integral. So the relation is very simple. The antiderivative function, if you want to write it as a function, f of x, will be the same as the area function, but will differ by a constant. Okay, so a given area function can be considered as a particular antiderivative with a particular starting point. The general antiderivative will be plus some constant. If you choose a different starting point, small a, then you get different area for the same x, right? But if you compare like two sets of such values, they only differ by a constant value. Okay. Explain mathematically, question 3, how the fundamental theorem of calculus is used to evaluate definite integrals. There isn't much to explain except what we have already seen here. Okay. What does the fundamental theorem of calculus say? It says the derivative of the antiderivative is the function itself, right? Basically, one of the statements. So How is that used to evaluate the definite integrals? Because um, what can I say? Let me put it this way. Because the derivative, or let me actually write dx, will differentiate in terms of x. Because the derivative of the antiderivative, right? This is from a to x is the function f of x. Okay. Using this idea, we say the definite integral from a to b of that function f of x dx will be the value of this antiderivative function, this function. This is f of x. Okay. Value of that function at f of b minus the value of the function at f of x. Okay. Um, I'll not go into more detail here. You can actually use the concept of definition of the derivative to on the function f of x actually. We can use the concept of derivative on the function f of x to prove this fact. Okay, using the fundamental theorem of calculus. Okay, I think that is too much of theory right now. Let me skip that. Next one. Between question 4 and 5, okay, I was looking at these questions earlier. They have some interesting concept here, okay? So just the concept, focus on that. In question 4 is kind of obvious, intuitive. If you have a constant function, you have to explain, okay, let me erase everything else. If f is a constant function, explain why the area function is an increasing function. That is the question, okay? So you would like think that's kind of obvious, right? Let's say, if I consider for simplicity a positive value of f like that, and I can choose any starting point a. Now, starting from here, the area function as x increases, as x moves to the right, the area under the graph will increase, right? The graph of this line is y equal to c. So this is an area function, obviously. It's an increasing function, clearly. Okay. More to the right, as x increases, the area under the graph increases. The second function question here says the function is f of x equals 3 minus x now. Okay. So let us draw the graph of 3 minus x. Not very difficult because the slope is -1 and the intercept is 3, right? So the points are going to be 0, 3 and 3, 0. Okay. So what does it ask us to do? Is its area function with left endpoint 0? So what they are saying is define this particular area function with the left endpoint 0. That means starting from 0 to x of that function f of t dt. Okay. So the question is it increasing or decreasing on that interval from 0 to 3? Okay. Now first to understand whether it is increasing or decreasing, let us understand what does it represent. This area function here represents the area under this graph from 0 to any variable point x, right? So for example, if x is at that particular point, we are talking about this area. And if you take the x to be a point a little further, then we are talking about that area and so on. Okay, you get the picture. From 0 to 3. So just that triangle, okay? Starting from origin until the point 3 comma 0. As you increase the value of x, what is happening to the value of a of x? Now you will say, obviously it is increasing. What's the doubt about that? If you cover more, you are covering a bigger part of the triangle, right? Ultimately, you get the entire triangle when you reach 3. So clearly it is an increasing function. The point is the f is decreasing. The function itself is decreasing, but the area is increasing. Okay, again, not like, not super surprising fact, but just like, with the diagram, it is kind of very obvious. But without the diagram, when we make a statement, it is something worth remembering. Okay, whether a function is increasing or decreasing, if its values are positive, then the area function for that region would be increasing always. Okay, and I'm talking about the net area function. Okay, remember the concept of net area and the total area. So when I'm talking about the net area, when the function is negative, the area function will be decreasing, because it will add negative values. When the function is positive, it will be increasing, no matter whether f itself is increasing or decreasing. Okay. So draw the picture and explain is what question says, and we have done that. Let me erase this. Okay. What's the next? Evaluate this. Again, this question is interesting, question number 6 here, because it shows us that, what is the difference between evaluating from 0 to 2 and negative 2 to 2. Okay. I will kind of like, give the answer here. Firstly, you will notice that like the function that you are integrating here is 3x square. So if the f of x is 3x square like that, then the antiderivative of it, right, should be x cube. Okay, the derivative of x cube is 3x square. So x cube plus c is the antiderivative function. So, for example, 0 to 2. Therefore, if you integrate from 0 to 2, that function, you will get f of 2 minus f of 0. Fundamental theorem of calculus, right? Used to evaluate the definite integral, f of 2 minus f of 0. And if you look at this here, x cube plus c, so you can see that is 2 cube minus 0 cube. Plus c and minus c will cancel. Okay, the constants will cancel, get 8. What about if you do minus 2 to 2? Integral from minus 2 to 2. Okay, of the same function 3x squared dx. Now this time it is 2 cube minus, right, minus 2 cube. F of b minus f of a. F of x is x cube. So minus minus makes it plus, and you end up getting 8 plus 8 equals 16. Okay, so the integral from minus 2 to 2 is twice of the integral from 0 to 2. Now, is that surprising result? No. Okay. Why? Because we know the graph of y equals 3x squared, right? That is a well-known graph. It's a parabola. It's going to be more broader than the, oh no, sorry. It's going to be more narrower. Made a mistake there. 3x squared. So it's vertically stretched by a factor of 3, like that. Okay. And if you take the area from 0 to 2, this is the area from 0 to 2. And obviously, the area from 0 to minus 2 is the negative part. You add them up, you get the total area. They're symmetric, basically. Hence, whatever result we get here makes sense, even graphically. Okay? Moving on. Evaluate this. Question 9 is again concept question. Look at the expressions very carefully. The first one is the derivative of the f of t dt integral from a to x. That is the antiderivative function, right? The area function. So clearly that is going to be giving you f of x. That's the fundamental theorem of calculus. Take the antiderivative and then take the derivative of the antiderivative. So you get the original function. Why? Because this expression here is the variable area function and its derivative, which area function is, of course, only a constant away from the derivative, from the antiderivative function. So the derivative of the antiderivative function will be the original function. Whereas the second expression, if you see here, has the derivative of a constant. That is important. Okay. Integral from a to b, where a and b are constants. So that the integral from a to b gives you a particular area. It's not a variable area. It's the area under the graph from a to b to fixed points a and b, and that particular area, which is constant. Okay. And so the second value here, this quantity is 0. Okay, the derivative of a constant is 0. Okay, that is the concept. Next, explain why the antiderivative of the derivative is this fb minus fa. Okay, is the original function, but the difference in the values of the original function because we are evaluating a definite integral. Okay. I'm not sure why the question says explain why. That is the basically the theorem or fundamental theorem of calculus in another way, put another way or another form of it. See, when you write small f as the original function, then the big F is your antiderivative, right? If your original function is small derivative of f prime, then the antiderivative is f. That's all it is. Okay. Otherwise, the statement is the same as the fundamental theorem of calculus as we stated in the books. Okay. All right. Next, evaluate from 3 to 8 of f prime t dt, integral of f prime t dt, where f prime is continuous. Okay, so remember we talked about integrability in the previous video. When is a function integrable? The general answer is quite complicated, but we do have some special cases, right? And one of the theorems, I think I would have shown that, is if a function is continuous, it is integrable. Okay. So being continuous is more stronger than being integrable. And I was giving you examples, right? When we say a function is integrable, we are asking a very loose condition. Okay. Only thing we want to guarantee is that you can find the area under the graph. Doesn't matter if the function is continuous or not continuous, as long as you are able to compute the area under the graph, it is integrable. So when it is continuous, it is clearly possible because a continuous graph, there is no break or anything. There is no confusion about what is the area under the graph. It might, depend on what techniques we follow. It may be easy, it may be difficult, depending on the function. But the area is a defined area, Okay. So when it is continuous, it is integrable. And f of 3 is 4, f of 8 is 20. Then it goes back to question number 10. Okay, it's nothing. Basically it should be f of 8 minus f of 3, right? 20 minus 4, which is 16. Okay. Evaluate the integral from 2 to 7 of 3 dx. Here the function is specific constant function given using the fundamental theorem of calculus. Okay. Using the fundamental theorem of calculus, you need to think what is the function whose derivative is 3, right? So if f of x is 3, what is the antiderivative? And you'll obviously say 3x, right? So the general one would be plus constant, 3x plus c. So then what is the value of this integral? It would be f of 7 minus f of 2. Okay, which is 3 times 7 minus 3 times 2, which is 3 times 7 minus 2, 3 times 5, which is 15. Okay, but one last time, we know this previously from the geometric interpretation as well. If your function is the constant function 3, that is the function here, y equals 3. That's the x-axis, so that's y equal to 3. So what is the area under the graph from 2 to 7? Of course, the width is 5 units now and the height is 3 units. So the area is 3 times 5, 15 square units. That is what is given by the definite integral. Okay. So those were some good questions to review. Let us begin some exercises here. Area functions. The graph of f is shown in the figure. Okay. And let the area function a represent the area starting from the point -2. So in the graph here, this whole thing. For example, if my x is, let me use a red color. If my x is here, then a of x represents this, like that. Okay, area starting from -2. This point here is -2. Okay, that is a of x. And what is f of x? Area from 4 to x. So this. Now, generally, I'm going to take x as a positive value. Okay. All right, let me actually show here. This is x, let's say. Some x here. Then f of x would represent only this area from 4. Okay, 4 to x. Let me write that out. Okay. Evaluate the following area functions. What is a of -2? I mean, evaluate the following values, they mean. A of -2. If you start at -2, from -2 to -2 will be 0. What is f of 8? Okay. So that will be the area from 4 to 8. And as it is given in the diagram there, that area is 9. Okay. The, I don't know, pink, light pink shaded area. Okay. Red, reddish pink. Okay. What is A of 4? A of 4 is this. Let me use the different color, green color. A of 4 is this whole thing, that this mound above the x-axis, right? From -2 to 4. And how much is given? 17 plus 8. That is 25. Okay. 8 here, 17 here. Add up, you get 25. F of 4, again, because you are starting from 4, f of 4 will be 0. And, oh, one thing I forgot to write clearly earlier. F of 8 is -9, not 9. Sorry about that. Okay. F of 8 is -9 because it is below the x-axis. I remember that now because if I have to compute A of 8, that is going to be this 25 minus 9. Right? 25 above the x-axis, 9. below the x-axis. That's 60. Okay. Fair enough. Um, where's my graph? Yeah. Sorry. Let me scroll carefully. The graph is given below and compute. Okay, this next exercise is similar. Okay, I'm skipping that. The area functions for constant functions. Okay. Consider the following functions and real number A. Find and graph the area function A to x of f of t dt. Okay, so the area would be a rectangle and it will just be whatever is the constant value of the function times the distance from A to x, right? There isn't much interesting stuff here. And they want you to find particular values in 15 and 16 here, okay? Let me look at question 15 and 16. In 15 and 16, they are looking for particular, like, values of f, okay? In this case, the height is 5 in 15, and you are starting from 0, A is 0, okay? So we are talking about this area from 0 to that. So the area would be simple. The area function a of x would be 5x. Okay. And if you start at minus 5, if you start at minus 5 instead of plus 5, okay, if you start at minus 5, then you have to add this also in the area. In that case, your area becomes 5 times x plus 5. Okay. Well, whatever x is, from x to 0 and another 5 units, right? The area is positive. Okay. That was the question there. Area functions for the same linear function. Okay. Consider the function. Okay, I don't know. I think there is some simple questions, but still, let me go through some of them. F of t equal to t. So we're talking about this graph. Okay. Y equals x graph. And what does it say? Evaluate A2 and A4. Okay. 2 is here. 4 is here. A of x is from 0 to x and f of x is from 2 to x. Okay, so A2 will be the area from 0 to 2 of that function t dt, right? F of t equals t. So that area is clearly, this is height is 2, width is 2. So the area is half times 2 times 2, which is 2. That is A of 2. Similarly, A of 4 would be half times 4 times 4. Okay, because on that triangle, x and y are going to be equal, the two sides of the triangle, which will be 8. Um, then use geometry to find an expression for a of x for x greater than 0. Okay, so now using geometry, what is the general expression for any x? Clearly, if this quantity is x, the graph is y equals x, right? So the general formula a of x is half x square, half x times x, okay? Which you can understand x square over 2 is the integral of x, right? You see where's the connection, okay? The integral of x is x square over 2 plus constant, and that is what we are getting geometrically also. And evaluate f4 and f6. Okay. Now for f4 and f6, because f is the integral from 2 to x, what's going to happen is you are going to be subtracting this area. This a of 2 that we computed, which is 2 unit, whose value is 2, uh, f of 2 is not going to count that, because it starts from 2. So I can clearly say the answer is going to be any of this. Like for example, f of 4 will be a of 4 minus 2. That the area of that small triangle, that part. Okay. And because a of 4 we have computed is 8 minus 2, going to be 6. And then what is f of 6? That's going to be a of 6 again minus 2. Okay, the difference between f of 2, f of anything, and a of anything is that small area over there. So half times 6 square minus 2, half x square, right? We have computed earlier. So 18 minus 2, 16. So that a of x minus f of x is a constant. Geometrically, just now I was saying the same thing, right? That and the constant value is this area 2. Okay. And because the difference of these two functions is constant, if you take the derivative, they will be equal. Think of that. Okay. A of x and f of x differ by a constant. When you take the derivative of the constant is 0. So the derivatives are equal, which is the function f of x. Okay. This is again all reviewing the concepts of derivative and antiderivative once again. I think the next question is similar. Area functions for linear functions. Okay. Again and again, we are trying to emphasize the same concept. The derivative of the area function gives you the original function. The area function itself is the general, is a particular antiderivative. A particular area function is a particular antiderivative. Okay. Okay. And moving on. Definite integrals. Evaluate the following integrals using following using the fundamental theorem of calculus. Explain why your result is consistent with the figure. Okay. Evaluate this using the fundamental theorem of calculus, it says. Okay. Mm, all right. Using the fundamental theorem of calculus, it is f of 1 minus f of 0. Okay. Where what is your f of x? F of x is the integral, which is going to be x cube over 3 minus x square plus 3x plus constant. Right? So if you plug that in here, you get 1 over 3 minus 1 plus 3. And then minus everything is 0, 0, 0. So minus 0, minus 0, minus 0, I'm going to say. Okay. So minus 1 over 3 plus 2, that becomes 7 over 3. Uh, Explain why your result is consistent with the figure. Okay, I don't know. The only consistent part I'm seeing is the value is positive we get here and is consistent because the area is positive here. Okay. And if you think about it, why it is 7 over 3 or which is 2 plus 1 over 3 basically, right? Before we did that. So you can see that here. Okay. The area of this part, let me actually erase the other stuffs and get into the concept of why it is consistent. Okay. The area of this rectangle part, okay, the height is 2 and the length is 2, length is 1. I mean, my bad. Length is 1, the scale is not correct. Okay. The length is 1, the height is 2, so the area is 2 here, 2 times 1. And the area of this part, this triangle has length 1 and height 1, but it's not exactly a triangle, it's less than like even the triangle, and looks like the area of that part is 1/3. Okay. And that gives you that area 2 plus 1 over 3. Okay. And I think I have about 2 minutes left. Let me look at the next question. Minus pi over 4 to 7 pi over 4. Sin x plus cos x. Okay. From here to here all the way. So that area is clearly going to be equal to 0. Okay. Now, if you ask me why, I would say the symmetry. Right? This part here, whatever you have, is going to be cancelled by the part below here. Okay. I think I'll stop at that here. In the next video, we will do more problems. See you in the next video.